One of the applications to consider for exponential functions is that of population models. Remember, an exponential function is just one that takes the form of f of x equals a to the x power, and that if a is between 1 and 0, the value of the function will decrease, and if a is greater than 1, the function will increase. Population is something that our world needs to be very concerned about because it does grow exponentially, and we have to take that into account when we're studying things like resources. The generalized form of an exponential equation that we use with population is shown here. Notice this is the f of x part, and this is a to the x power, but instead of x, we're using t. This portion here is not p times t, but rather p of t, and it refers to the population at time t. This p naught is all one term, and this refers to the original population, so what we start with. The a we refer to as our growth factor. So if a is greater than 1, the population is increasing. If a is less than 1, it is decreasing. And t is our time, typically measured in years, but it can be measured in hours or minutes, as we'll see in our next example. Let's consider this problem. A biologist is culturing a bacteria in a petri dish. She begins with 1,000 bacteria, so this is her initial population, and supplies enough food so that for the first 5 hours, the population grows exponentially, doubling every hour. We want to find this function, p of t equals p naught of a to the t, that models this equation or this situation. Our initial population, again, we know is 1,000. And the only other information that we have is that it's going to double every hour. So after 1 hour, p of 1, the population will be 2,000. We can plug this information in then to find a. We have p of 1 is 2,000 is equal to the initial population of 1,000 times a to the t value, and that's after 1 hour. We're going to divide both sides by 1,000, leaving us with 2 is equal to a to the first power. Notice this is the same as 2 to the first. So since our exponents are equal, our bases have to be equal, and a equals 2, giving us the equation that p of t is equal to 1,000 times 2 to the t power. For the second half of our problem, we want to know when the population will reach 16,000. That's a p of t. We want to know the when, which is the t value. So we take that 16,000 and then we substitute into our original equation that we calculated, dividing both sides by 1,000. We get that 16 is equal to the t, and using our skills for solving exponential equations from the previous section, we have to equate our bases. 16 can be written as 2 to the 4th is equal to 2 to the t power. Since our bases are equal, our exponents have to be equal, so it will reach a population of 16,000 bacteria after 4 hours. The last part of this question says calculate the population 2.5 hours after the scientist begins. In this case, we want to know a p of t. So we take our equation, that 1,000 times 2 to the t power, and this time we know t. So we have 1,000 times 2 to the 2.5 power, and we calculate that to be 5,657 bacteria.